Okay, let's look at double replacement reaction. So this is a chemical reaction where two compounds will trade cations with each other. Now remember that the cation is listed first and the anion is listed second in an ionic compound, for example, or an acid or a base. Okay, so ionic compounds are made of positively charged ions called cations, and they are bonded to negatively charged ions called anions. And when the cations switch, a new set of compounds is formed. Okay, and there are three different categories of double replacement reactions. The first one is precipitation. Precipitation reactions will form a solid product. So you would have to look at the state of matter. So let me give you an example. Do you see this reaction down here? NaCl plus AgNO3 produces AgL solid. This solid would be a precipitate. And in section 4.1, when we talked about the different forms of evidence that a chemical reaction occurs, this is one. Okay. The second type of double replacement reaction is called a neutralization reaction. And you guys have actually already done this in a lab. So neutralization reactions are when you combine an acid and a base and it should feel a little bit warm after you combine it, which is a form of evidence that a chemical reaction occurs. And then the acid and the base will produce a salt and water, okay? The last type of double replacement reaction is called a gas formation reaction. So that means one of the products will be a gas. Okay. We're good? Okay. Let's come down here. And this last reaction here that I want to mark up, what color did I do up above for the neutralization reaction? Blue? Okay. So this is a neutralization reaction here. So what they did here was they combined sulfuric acid, which is a strong acid, with potassium hydroxide, which is a base, and they made a salt. Remember, salts are ionic compounds. We talked about this in chapter 2, and water. And they put heat as a product to emphasize the fact that neutralization reactions produce a detectable amount of heat. Okay, so that means they are exothermic since heat is being released. And this is also your form of evidence that a chemical reaction occurs. That's it for that page, correct? Okay, let's take a look. There should be, did I take out the practice problems or are they still there on the next page? They're still there? No.
It's like at the bottom.
So over here, is this in your book? Okay, let's take a look at this. All right, they want us to classify the types of reactions that we have. So meaning synthesis, decomposition, single replacement, double replacement, or that's it. So for number 1, what kind of a reaction would this be? So just to give you an idea, double replacement is abbreviated DR typically, and you're going to have 2 compounds combining. The cations trade places, and you're going to form 2 new compounds. So that's your generic double replacement reaction, okay? So based upon that, do any of 1 through 4 look like a possible double replacement reaction?
Yeah.
Can you tell me what number 2 is? Yeah, single replacement. And that's because you have an element combining with a compound. Okay, so we know that one. How about number 4? Single replacement. Okay. So now let's go back to 1 and 3. What do you think those are? Yeah, those are double replacement. Okay. We're not going to do number 4, like we're not going to predict the products and write a balanced formula for it, but let's do 1, 2, and 3, okay? So what I'm gonna do is I'm gonna highlight the hydrogen and the iron in number 1 because those are the cations, yeah.
I was wondering, how do we know that it was a single replacement?
Because single replacements are when you have an element combining with a compound.
Okay.
Okay. What we want to do here is we want to write this out in words. So instead of writing this as hydrochloric acid, we're going to write this as hydrogen chloride. It will make it easier when we decide to predict our products. And then this is iron 3 hydroxide. You determine the Roman numeral on iron because you have 3 hydroxides at a -1. Okay, hydroxides on the bottom left of your periodic table. When you multiply these together, you get a -3. That means you need a +3 on the other side. But since I have 1 iron, 1 times +3 would give me that +3. So this is the charge on the metal or the Roman numeral. Okay, we did that in section 2.4. So we're going to switch, bless you, the hydrogen and the iron 3. Make sure you keep that Roman numeral with the iron because it goes with it. Okay? So when those switch, you're going to form iron 3 chloride plus hydrogen hydroxide. Okay? All right, iron 3 is Fe plus 3. What's the charge on chlorine? -1. Do you all have your nomenclature periodic table out? If you don't have one, go get a laminated one, okay? Because you need to reference it when you're doing all of these. So what would my neutral compound be? FeCl3. So this is FeCl3 plus hydrogen hydroxide is another name for water because hydrogen has a +1 charge, hydroxide has a -1 charge. So you just need 1 of each. So you're making HOH or water, okay? And this isn't balanced. You're gonna need a 3 in front of here to balance this hydroxide with the 3 on the other side. And then you have 3 hydrogens, so you would need a 3 here to balance the hydrogen. Then you have 3 chlorine, and now you're done. 3, 1, 1, 3 would be the appropriate coefficients, okay? Let's take a look at number 3. That's another double replacement, okay? So what should I highlight in number 3? What's going to switch? NH4 and what? CS. Okay. So I've highlighted those. Now let's go ahead and write this out in words. So this is on the lower left corner of your periodic table. NH4 is ammonium. So this is ammonium sulfide plus cesium hydroxide. Okay, and I'm going to go ahead and highlight the ammonium in words and the cesium in words because that's what you want to switch places. Okay. So when they trade, I produce what in words? Yeah, cesium sulfide. And what else?
Ammonium hydroxide.
Yeah, ammonium hydroxide. Okay, now we need to look at the nomenclature periodic table to figure out what the charges are for everything. So cesium has what charge? +1. Sulfide has what charge? -2. So what would my neutral compound be?
CS2.
Yeah, CS2S. Ammonium is NH4 +1, is on the bottom left next to hydroxide, which is OH -1. So wouldn't I need one of each to make my neutral compound? So this would just be NH4 OH. And this is not balanced, unfortunately. You've got 2 cesiums right here. So I would put a 2 here to balance the cesium. Then you've got 2 hydroxides. So I would put a 2 here to balance the hydroxide. And then you've got 2 ammoniums. Well, you already have 2 ammoniums over here, so you're done. It's 1, 2, 1, 2 for the coefficients. Okay. Okay. So you've got a worksheet on double replacement reactions. Okay. So you're going to write everything out in words first, and then convert the words to formulas and balance it, and like highlight things as you go, just like I did, to make sure that you get the right products. Does that make sense?